Welcome back, and let's try 9.6, identify symmetry today. We have two types of symmetry we're going to look at with our figures. The first one is line symmetry. Line symmetry is when a figure can be mapped onto itself by a reflection in a line. Sometimes I like to think of this as when you can fold an image onto itself. So if we think about this is where we're going to fold an image onto itself. You were probably familiar with this when you were in kindergarten or younger grades, when you would make that butterfly and you would want it to look identical on both sides, or maybe you folded your paper in half and drew half a heart and you cut it out that way. So your line of symmetry would be that line of reflection in a figure, or the fold line. So if you did your heart or your butterfly, that would be that line down the center. Our second type of symmetry is called rotational symmetry. And this is when a figure can be mapped onto itself by a rotation of 180 degrees or less. This is when you can turn an object onto itself. And that center point where you turn it at is called your center of symmetry. So that's our vocab here. Let's just get started on our examples. That's really the whole idea behind this whole lesson today. So we're going to start with identifying lines of symmetry. So if you think about it, when you look at a figure, you're trying to decide, can I draw a line through this figure that when I fold on that line, all of my lines on both sides should line up exactly. So in this first rectangle, we could definitely do this horizontal fold here. So when I fold top to bottom, they would be identical. Or I can do this vertical fold here because both left and right side would be identical. So those are both lines of symmetry. Now, sometimes students like to tell me that, well, we could go diagonal to diagonal. But if you're thinking that, I challenge you to pick up a piece of normal paper, a rectangular piece of paper, and try to match that diagonal corner to corner and see if you actually get that paper to be exactly on top of itself. And you'll find out that you don't. So for a rectangle, we're going to have to stick with just two lines of symmetry. Our next figure we're looking at is a regular pentagon. And I do want to stress to you, this is a regular pentagon. All the sides are the same length and all the angles are the same measure. And because of that, we can make multiple folds or multiple lines of symmetry in this figure. I'm going to start with one that maybe you wouldn't draw from this direction to start with, but I want to make sure you're kind of seeing this. I can go sideways here from this vertex across to the line across from it. And because of that, I can keep going from every vertex to the line straight across from it in the center, vertex to the line straight across, vertex to the line straight across, and vertex to the line straight across. Okay, and I know all my lines aren't perfect here as I'm trying to draw these, but you can kind of get that idea. Now, one thing I want to warn you about is don't count all these spokes you see, but think about starting at a line like line 1 here. I can count line 2, line 3, line 4, line 5. When I get to this one, it's going to be the same line as line 1, so I don't want to count it over. So it looks like I have 5 lines of symmetry there on that regular pentagon. Now on C, my final one on this example, is also a pentagon, but you'll notice it looks more stretched out. My angles are not all the same. My angle at this top right here, that looks a lot wider. Make sure I'm drawing this here. This angle up here looks a lot wider than the one did over here. So definitely a different looking pentagon here. So I can definitely draw this vertical line down the center, but that's where I have to stop. No other line can I draw where when I fold, I'm going to have identical on both sides of the line. So in this pentagon, I only have one line of symmetry. So it definitely makes a difference if it's regular or if it's not. And be warned, there are figures that have no lines of symmetry. So don't always think that you can find a line of symmetry. Let's turn the page and try our rotational symmetry. So we're going to start here with rotational symmetry. And rotational symmetry, if you can see in the margin, I gave you some notes. You're going to ask yourself, how many times can I turn it until it's back in the starting position? If it's less than 180, or I should put or equal to, because it doesn't have, it could be exactly 180. Then it has rotational symmetry. So that's the key. Can I turn it exactly 180 or less? and it still looks like itself, then it has rotational symmetry. And if it does have rotational symmetry, then what we want to do, and I'm not sure why I have this so out of order, we're going to divide 360 by the number of times I can turn it to find all my angles of rotation. And I'm going to be picky here. I want this on every homework, on every quiz, on every test. I want you to list all the angles of rotation all the way up to 360 degrees. So let's look at our first example A here, the square. And our center of rotation is in the center of the figure. So there's my center of rotation. So it's like if I put a pencil right there and I turn this page, how many times could I turn it and it looks like the exact same square? I like to visualize it here that I start at this vertex. If I move this vertex to this corner, it'd still look the same. If I move it to this corner, it would still look the same. If I move it to this corner, it would look the same. And if I move it to this corner, it would still look the same. So it definitely has rotational symmetry. And it looks like what I would do then is take 360, and I could move that 4 times till it went back to its original. So 360 divided by 4 will give me my angles of rotation. So 360 divided by 4 is 90. If I add another 90 onto that, I get 180. I add another 90 onto that, I get 270. And finally, I add another 90 and I'm up to 360. So I'm going to stop once I get back to 360. So those are my angles of rotation that will, I can turn this square that many angles or that many degrees and still land back on itself. So that shows me rotational symmetry. Now let's move to B, my regular hexagon. And again, I want to stress to you, it does say that it is regular, so all my angles and my sides are exactly the same length. So again, I find my center of rotation, and I try to see how many times can I turn this hexagon and it'll look identical to itself. So once again, I'm going to choose a vertex, and I'm going to choose I could turn it once here, twice, 3 times, 4 times, 5 times, and 6 times. So once again, I'm going to say that definitely this hexagon, regular hexagon, has rotational symmetry. And I'm going to take 360 and divide by the number of turns, and I was able to make 6 turns, and it landed back on itself. So 360 divided by 6 is angles of 60. Add 60 more to that, I get 120. Add 60 more to that, I get 180. Add 60 more to that, I get 240. 60 more than that is 300. And 60 more than that takes me up to 360. So there's all my angles of rotation for my regular hexagon. So my third and final example here for my rotational is this kite. So once again, I'm going to go to this kite. My center of rotation would kind of be in the center of it. And I'm looking to see, can I take this vertex here, and when I turn it, where can I stop and it looks identical to itself? Well, it looks like I'd have to go all the way back to the original before I could turn it and it looks identical to the same kite I started with. Since I have to go more than 180 degrees to make that kite look back like itself, this kite has no rotational symmetry. There's no degrees of that. So no rotation of 180 or less will map the kite back onto itself. So there's no rotational symmetry. So let's move down here to example 3. And this one's going to do a little mixing of my line symmetry with my rotational symmetry. So we're going to start with the line symmetry. When I look at this, it says how many lines of symmetry can I draw through this figure? So I draw one that's horizontal, and notice they have them drawn for us here, and one that's vertical. These are the only 2 lines I can draw where the figure will map back onto itself in both directions and it looks identical. So this figure definitely has line symmetry, and there are exactly 2 lines of symmetry that can be drawn in that figure. Now, this next box is what's kind of nice and important, and it will help us in future examples. It says for a figure with S lines of symmetry, the smallest rotation, so here we're going to mix rotation with our lines, that maps the figure onto itself has the measure of 360 divided by S. S is the number of lines of symmetry. So in this example, if we do 360 divided by our 2 lines of symmetry, I know that I have rotational symmetry of 180 degrees. And if I look at this figure and I say, here's my corner, where would I have to turn it till it maps back onto itself? I would have to draw it here, and then again I could go all the way here. So there's exactly twice, which matches this 360 over 2. So just kind of a recap of what this is telling me I can do. I can take 360 and divide it by my number of lines of symmetry. And that will equal the angle of rotation. So if you're having trouble finding or saying what would be my angle I want to rotate, if you can draw lines of symmetry first and take 360 divided by that number, then you'll also find the angle of rotation. Moving on to our last and final page here. It's a short set of notes for this section. So we're going to start at the top here, and we're going to find from 1 and 2 how many lines of symmetry we can draw on each of these figures. So our first one is a trapezoid. It looks like it could be an isosceles trapezoid here. I can't draw a horizontal line because the bottom is shorter than the top, so I wouldn't be able to fold it on top that way. But I could draw one vertical line here because the left and right side are identical. But that looks like that's all I can do, so I have one line of symmetry on this one. On my next figure, looks like it could have a rhombus or a square, looks similar here, and I'm looking to see how many lines of symmetry I can make on this one. So I could go vertex to vertex, my horizontal line here, vertical vertex to vertex, but I can also go middle of the side to middle of the side and middle of the side to middle of the side. So just like in that earlier example, be careful counting your lines here. If I start here, 1, 2, 3, 4, this one's back to my original. So it looks like I have 4 lines of symmetry. All right, moving on to 3 or 4, we're going to switch back to rotational symmetry. Okay, so I'm looking here and I'm saying, can I rotate this figure and it lands back on itself? So I'm going to actually look at this kind of center point that's easier for my visual. If I map it, I could turn it right there. It could land right there. It could land there. It could land here. Or it could land here. So definitely I have rotational symmetry. I take my 360, which is a full turn, and I divide by my 4 turns. And it looks like I could have angles of 90. Add 90 again to that, and that's 180. Add 90 again for 270. And finally 90 again, and I get my 360. So I have to stop there. For number 4, I'm looking at a triangle. It looks like this is an isosceles triangle. It appears that the 2 legs on the side are the same length. But I'm looking at the top here and I'm saying, if I try to turn this, how far do I have to turn this point till it looks back at itself? And it looks like I'd have to start turning and turning and turning, and I couldn't stop till I get all the way back. Because my turn is more than 180 degrees, I have to say no rotational symmetry. So that's on an isosceles triangle. Before we do number 5, I want to go to the margin. I'm going to draw a different triangle here. Again, I'll try my best to draw this here. If I draw an equilateral triangle, okay, if I draw this equilateral triangle, does the equilateral triangle have rotational symmetry? We just looked at an isosceles triangle. It had no rotational symmetry. But if I change it to an equilateral, will I have any rotational symmetry? And the answer here is yes, I do, because I can take this vertex and I can move it to here, and then I can move it to here, and then I could move this one to here. So I do have that. So I do my 360, and change to an eraser here. 360 divided by my 3 turns, and I can turn it 120 degrees. 120 more than that is 240 degrees, and 120 more than that is 360 degrees. So that one does have rotational symmetry. So don't rule out or think all triangles are the same. It depends if you have an isosceles, if you have an equilateral. If you had a scalene triangle, you couldn't turn it at all either. So every type depends on the type of the drawing you have. All right, and we're ready for our last and final example here. So on our last one, we're trying to find our lines of symmetry on this star. So once again, I'm going to try my best here to draw these. They're going to be tricky because there's going to be so many. But we're trying to find where could I fold it and it looks identical from top to bottom, or left to right, or side to side, however we draw this line. So it looks like I could draw a horizontal one here. I have my vertical one here. But I can also go anywhere point to point. So I can draw one here, and I can draw one here. But that's not all of them I could draw. I could also go into those indents in between and also fold there. So another one there, another one there, another one there, and finally one more there. And I apologize for how much I'm not exactly in the spots I'm telling you to draw them in. Once again, it gets tricky to count, and I'm going to number mine. So I have 1 here, 2, 3, 4, 5, 6, 7, 8. When I get to this one, it's the same as I started on 1, so I'm not going to count any further. So I have 8 lines of symmetry. Trying to make my paper a little bit bigger so I can write this easier. Okay, notice now it also wants me to talk about my angles of rotation. On the same picture, do I have angles of rotation? So if you think about it, if I'm trying to move this tip here, and I can move here once, then to here, then to here, then to here, to here, to here, to here, and then again to here, okay? So if we do that, my 360, and it looks like I turn that 8 times. If you have trouble drawing these turns, or like my picture here is getting pretty confusing to do this, remember the note from the page before that said you can take 360 and divide by your numbers of lines of symmetry, which is 8, so you'll notice those two numbers match each other, and you can divide by that to also get your angle of rotation. So 360 divided by 8 is 45. So if I go to make my list, I have 45. 45 more than that is 90. 45 more than that is 135. 45 more than that is 180. Plus 45 more is 225. Plus 45 more is 270. Plus, can't read that one. Just give me a minute here. $270. 45 more than that is 315. And 45 more than that is 360. So I have my final list here. So 8 angles there when there's 8 lines of symmetry, or 8 times I can rotate that. And that's your lesson for symmetry with our line symmetry and our rotational symmetry. So your homework is to do 9.6 worksheet. And I do want to make sure you know that anytime you list angles of rotation, please list them from the smallest all the way up to 360. And remember, you can always use that hint that the number of lines of symmetry is the same number of times you can rotate it under 360. So you could do 360 divided by that number. So good luck on the 9.6 homework. Please email me if you have any questions, or you can always write a question in the stream too if you think someone else will have the same question. Good luck, and I'll see you for the next set of notes.